Okay guys, thanks for tuning in on this one. I really want to kind of get us caught up, so thank you very, very much. I really appreciate you doing this and going and looking at this at night. We're going to start right here on page 3. We're going to plot this graph of f of x is x cubed plus 7 over x squared minus 4. And on your calculator, this is what it looks like. We want to transfer this onto paper. Clearly the numerator is not going to factor. The denominator will factor into x plus 2 times x minus 2. Since the numerator factored, or wouldn't factor, I'm sorry, those factors in the denominator, x plus 2 and x minus 2, are not going to cancel out. So we have vertical asymptotes at x equals 2 and at x equals negative 2. If we go ahead and sketch that graph onto paper, vertical asymptote here at x equals 2 and here at x equals negative 2. We very definitely see a oblique asymptote in here running right through there. You should see that. We can find out exactly what that oblique asymptote is by doing some long division, and we do have to do long division here, not synthetic division, because our divisor is quadratic. In order to do synthetic, we need to have a linear divisor with a leading coefficient of 1. Don't forget the placeholders in here. When we divide this out, x squared into x cubed goes x times, and we multiply. That gives us x cubed minus a 4x. Subtract. 0 minus a minus 4x is 4x plus 7. That is the remainder. X squared will not go into 4x. So this x cubed plus 7 over x squared minus 4 can be rewritten as x plus 4x plus 7 over x squared minus 4, which tells us this remainder portion is not going to be important for us with this oblique asymptote. The oblique asymptote is the linear portion, and that is y equals x. If we go back to the graph and put in y equals x, we can pick up a y-intercept here. Y-intercept is going to be at negative 1 3/4. And then just sketching the rest from your calculator, we can see a 0 right around negative, real close to negative 2. Can't be at negative 2 because we know we have that vertical there, so it must be just a little bit prior to negative 2. And sketching in, we're seeing something like this. And this piece up here, and this piece down here. And there's our sketch. This one's a little bit different in terms of the rest of the problem because of the wording that I used. Instead of identifying the discontinuities, we're going to be identifying where the function is continuous. So we would say this function is continuous on the interval, well, from negative infinity up to negative 2. Open on both ends, union, also continuous between negative 2 and 2, open on both, and again, continuous from 2 to infinity. There are no breaks, gaps, holes, asymptotes, anything within those 3 intervals. Between the intervals, absolutely, there's vertical asymptotes, but not within each interval. And the last part here, identify the types of discontinuities. Well, they is discontinuous at x equals 2 and x equals -2. Both of them are essential, infinite discontinuities. Okay, last one here. I want you to sketch a graph of this function. G of x is x over x minus 2. Identify its domain, and then figure out if g of x is continuous on the following intervals. Quickly, nothing factors, nothing divides out, so we have no holes. We see a vertical asymptote at x equals 2 from the denominator. We see a horizontal asymptote at y equals 1 from doing the limit as x approaches infinity, fraction of the leading coefficients, because the degree in the numerator is the same as the degree in the denominator. So we have a horizontal asymptote at y equals 1. When x is 0, y is 0, so we're going to hit right here at the origin. And using our asymptotes, we can see this graph generate like this. On the other side, from pre-calculus, we know that it has to go up this way. Can't go underneath, because if we were underneath, we would have to hit the x-axis, and there are no other zeros. There's the graph. Domain, x cannot be equal to 2. All right, now look at these intervals from -infinity up to and including 0. All of that. -infinity up to and including 0. Is your function continuous? Yes. How about starting at 0 up to positive infinity? That much. Nope, because we have a vertical asymptote here at 2. How about the interval from 0 to 2, open at both ends? So that's just after 0 to just before 2. Yes, that one is continuous. How about just after 2 all the way up to and including 2? That one's no. Function's not defined at 2. Can't be continuous there where it's not defined. How about starting at 2 up to infinity? That one's no. Okay, and for this last one, I want you to adjust this interval at e ever so slightly to make the answer to that question be yes. How can you adjust e so that it is continuous on that interval? Yes, you're right. Open at 2 up to infinity. And that's it. Perfect. Thank you so much for tuning in and getting this done ahead of time. We will pick up right here on, oops, wrong page. That was an extra one. We're going to start on page 4. Here it is. On page 4 on tomorrow's Thursday. Perfect. Thank you. Then we're just one question behind, but we can pick that up on the same day that we do intermediate value theorem. Thanks again. See you tomorrow.